Now, any questions on how do we determine the signs? I mean, as time goes on, it will become more and more complicated, so make sure that when we are discussing, you understand why we choose a particular sign or the other one. Now, let's look at what's called the multi-loop circuits. Now, we had already studied one simple one, where we have many resistors connected in parallel. And there is a battery over here. Let's also add the internal resistance of the battery. R1, R2, R3, and small r. Well, you probably already know that if this system has the equivalent resistance of R plus 1 over R1 plus 1 over R2 plus 1 over R3. So basically, these three resistors have an equivalent resistance given by the inverse of the equivalent resistance of all these three is this sum. And these three resistors are connected in series with this one. So that's why we add this large R. Now let's derive this one using what we already have seen. Now let's first choose some directions for our currents. Let's say this is my current running through this wire. Let's say this is the current running through this one, I2. No, let's call this I1, I2, and I3. So in this wire, the current running is I2. In this wire, it is I1. In this wire, it is I3. In this wire, it's the capital I. So there's no reason why they should be equal or different or etc. We will be calculating each one. Let's again give some names: A, B, C, D, E, F, G, and H. This has the EMF. Let's say epsilon. Let's start with VAA. This should be 0. Now VAA, we can write it as VAB plus VBG plus VGH plus VHA. This is called one loop. So I start from here. From A, I go to B, from B to G, from G to H, and H back to A. This is one loop. A, B, B, G. Now, what is the potential drop as I go from A to B? The current is I times R. I times R. Now, what is the potential drop as I go from B to G? I3 times R3. From G to H, that is 0. From H to A, potential drop, minus epsilon, because A is at a larger potential than H due to this battery. A is the positive terminal, H is the negative terminal. So the potential is in fact increasing from H to A by epsilon, but an increase in epsilon is the same thing as a plus epsilon is the same as minus epsilon. So the potential drop is minus epsilon. So and this should be 0. So I have one equation. You see, here I have 4 unknowns. I don't know I1, I2, I3, or I don't know I. There are 4 things that I have to determine. Now I have one relation relating these unknowns. But of course, since I have 4 unknowns, I need 4 equations, at least. So this is one of them. This tells me that I times R plus I3 times R3, this is equal to epsilon. Let's try to find one more. I can still look at VAA. But this time VAA, I can write it as I go from A to B, from B to C, from C to F, from F to G, from G to H, from H to A. This is another loop. So in the first example, I started from A, B, G, H, and back to A. Now I'm going from A, B, C, F, G, H, and A. 3 ones here? Which one? Here. A, B, B, C. F. Okay. Now after F, that's all F. So I was just checking whether you were asleep or not. He's awake. Okay. VAB. The potential difference drop as we go from A to B. It's I times R. From B to C, 0, there's no resistance. From C to F, I2 times R2. From F to G, from G to H, from H to A, minus epsilon. So this is our second equation. I times R plus I2 times R2, this is equal to epsilon. Now I will continue. This is the second equation. We still need 3 more, 2 more. Again, I can look at VAA. This time this will be from A to B, from B to C, from C to D, from D to E, E to F, F to G, G to H, H to A. What I'm doing is I'm just going all around this one. A to B, B to C, C to D, D to E, E to F, F to G, G to H, H to A. Let me copy this. This is my circuit. Now, this is, I'm looking at VAA still, which should be 0. What is VAB? It's always I times R. BC, 0. CD, 0. DE, I1 times R1. EF, FG, GH, HA, minus epsilon. So we have IR plus I1 R1. This is equal to epsilon. And this is our fourth loop. So we have, okay, I times R plus I2 times R2. This is equal to epsilon. I times R plus I3 times R3. This is equal to epsilon. Now we need one more. Still one more. Well, we don't know I1, we don't know I2, we don't know I3, we don't know I. That's the fourth one. Well, let's see. Let's try VBB. which should be 0. This is VBC plus VCF plus VFG plus VGB. What is VBC? 0. VCF, I2 times R2. FG, GB, minus I3 times R3. Why minus? Well, let's see. If I3 is positive, that means B is at a larger potential than G. So from G to B, we have a potential increase, which we can write as a negative potential decrease. So if I3 is positive, then the potential drop is a negative number, so we should add that minus. So this tells me that I2 R2, this is equal to I3 R3. But in fact, if you just look at these two equations, if you subtract these, you get the same equation. This is not an independent equation. These three equations already tell me that I1 R1, this should be equal to I2 R2, this should be equal to I3 R3. These three equations, I can just replace them by these two equations over here plus any one of them. So this didn't give me an independent equation. I need an independent equation. Well, the independent equation comes from energy conservation. Now let's look at this point. Let me say that this is I3, this is I2. I just invented some new names. No, I don't need this I2. The current running through this circuit through this line is I1. Let's say this is I3. So let's look at this one over there, this point B. The current I is coming in. The current I3 is coming out. And the current small I3 is coming out. So we said that the current is nothing but the charges per unit time. That's how we define the current. So if we wait a unit time, the total amount of charge that enters this point is I. In the same unit time, the amount of charge leaving this point is capital I3 and small I3. If charge is conserved, plus we are studying steady currents, which means there is no accumulation of charge anywhere, this point was neutral, is still neutral, then whatever charge enters at the point B should also leave the point B. So that just tells me that I should be equal to small I3 plus large I3, which tells me that this large I3 is capital I minus small I3. We agree? So basically, if you consider any point, the sum of the currents entering that point should be equal to the sum of the currents leaving that point. Again, this is just the consequence of charge conservation plus the fact that we are considering systems that are in steady state. That is, they do not change in time. There is no accumulation of charge anywhere except on the capacitors. So there shouldn't be any accumulation of charges at this point. Okay, so that gives me what this I3 is in terms of the other unknowns. Now let me look at this point C. At the point C, I have I3 is entering. This is I3. This is the point C. I1 is leaving. And also I2 is leaving. Again, if you just sum the currents that are entering this point, that is just I3, should be equal to I1 plus I2. So this is the total current that is entering this point. This is the total current leaving that point. This is just, by the way, just scalar sum. We are not adding them vectorial, just the numbers. Because basically what we are equating here is the number of charges. If there are 5 electrons leaving this point due to this I3, there should be 5 electrons entering this point due to this small I2 and small I1. Yes. That's what I'm repeating now. The current is a scalar quantity, it's not a vector. Although we are putting arrows, we are just choosing positive and negative currents. And so if you combine this with the previous results, this just tells me that I should be equal to I1 plus I2 plus I3. So this is my fourth equation. I had 4 unknowns. Now I have 4 equations relating these 4 unknowns. And the next is just do the algebra and solve for the currents. Yes, questions? Questions? Why didn't we choose? So let's see, VCC, it should be 0. How should I go? What kind of a loop would you like to have that starts from C and goes back to C? VCD, VDE, VEF, and then back? Okay, VFC. Let's look at this one. What is the potential drop as we go from C to D? 0. From D to E, potential drop? I1 times R1. From E to F, the potential drop? 0. From F to C, the potential drop? Minus I2 R2. So this tells me that I1 R1 should be equal to I2 R2. But this is something that I already knew. Here. Oops. So here we already knew that from these 3. Now the remaining loops don't give you independent equations. I mean, you can just consider any point over, you can just consider any loop starting from an arbitrary point going back to the arbitrary point. And what you will obtain will be an equation, either these ones or an equation that can be written in terms of these ones. You don't get a different one. Now, to find the necessary remaining equations, you use you use the conservation of the total charge. Epsilon 1, epsilon 2, epsilon 3, R1, R2, and R3. Which way will the current go? In which wire? So you see, if epsilon 3 is strong enough, that its EMF is large enough, we know that the current in this wire will be in the counter in this direction from right to left. But from this point on, does that current split into part of it goes in this direction, part of it in the other wire, or there is another current in this wire that's going upward that goes towards both of them combined that goes to E1? We don't know. We have to solve for them and determine even the directions of the currents. And beforehand, we don't know the directions. Do you like the clockwise sense or the counterclockwise sense? Okay, how many of you like the clockwise sense? How many of you counterclockwise direction? Well, clockwise is larger. Okay. So let's choose this direction as the positive sense of my current. Let's call it I1. This as the positive direction of my current I2. And let me do something else. And this is my current I3. Okay, I have three unknowns. I have to determine these three unknowns. So I have to write three equations for these three unknowns. Let me first write the equation for the for the charge conservation. Let me look at this point. What is the total number of, what's the total current that is entering this point? That is entering this point. 0. There is no current entering that point with these directions. What is the sum of the currents leaving that point? I1 plus I2 plus I3. So the sum of these three currents have to be 0. So already this tells me that at least one of these currents should be negative. At least one of them. So before you complain that how come all the current is leaving this point, not all of them are leaving that point. At least one of them should be entering. So this is what this statement is. One of them should be negative. That is, it should be running in the opposite direction. So let's just choose this point. I mean, you can just choose arbitrary point and just go around any loop that you like. Now, for simple, I just chose this one for no particular reason. I'm left-handed, so it's on the left. And we can choose to go around, as I said, any loop in any direction. So since the majority said counterclockwise sense, so let's start from this point, go counterclockwise in this small loop. Okay, now, as I go from this point to this point, what is the potential drop? Nothing. From this point to that point, the potential drop? No, from this point to this point, sorry. I'm just running across this resistor with resistance R2. 0 should be equal to minus I3 R2. Why? Because if I3 is positive, from this point has a larger potential than this one. So as I go from this one to here, I'm going over a potential increase, which is a negative potential drop. So if I3 is positive, the potential drop is negative. I look at here, I3 is positive, R2 is positive. If I3 is positive, the potential drop should be negative, so I insert that minus 1. Across this battery, what is the potential drop as I go from here to there? Minus epsilon 2. There is no potential drop, there is a potential increase, but a potential increase is a negative potential drop. Okay, so this is the potential drop as I go from this point to this point. Okay, from this point to this point, what is the potential drop? There is no resistance, so there is no potential difference. And from this point to this point, what is the potential drop? Plus epsilon 1, because I'm going from the positive terminal to the negative terminal. And from this point to this point, what is the potential drop? I2 times R1. Is it plus or negative? Minus. It should be plus because if I2 is positive, that means the current is running from this point to this point. Across a resistor, the current runs from the higher potential to the lower potential. So this is at the larger potential than this point if I2 is positive, and I2 times R1 is already a positive number, so I don't need to insert any minus signs. Arbitrarily? Well, you said that, I mean, at least some of you said that you like the counterclockwise sense. Well, I just chose the counterclockwise sense, let's say, in this circuit, in this wire, in this current. Well, to be fair to those who like the clockwise sense, this is the one that grounds in the clockwise direction.
So half of this, half of this, is very arbitrary.
And then just to confuse you a bit, I just chose the direction of I3 in this one. Completely arbitrary. Well, if you are a professor, a lecturer, then it completely depends on how mean you would like to be.
How did this be right? Such direction of the current is right?
I don't know. I mean, there is no, you see, in the choice of the positive direction of the current, there is no right or wrong. You just choose whichever directions you like as the positive direction of the current. But this equation already told me that at least one of the currents is not running in the positive direction. At least one of them is going in the opposite direction, to the chosen directions. But in the choice of the positive direction, there is no right or wrong. It's completely arbitrary. It's up to you, whichever one you like. It's just like in choosing, I don't know, in the mechanics course, in the one-dimensional motion, we chose this direction as positive. It's not right or wrong. It's a choice, arbitrary choice. You could have as well choose the other one, positive. It's the same over here. I chose this direction to be the positive direction for the current I2, but I could as well have chosen the opposite direction as the positive direction of I2.
Peki yönleri bu şekilde kalsa, gerçi I2 artı pozitif diyebilir miyiz bilmiyorum ama onun sign'ı değişse I2 R1'ı negatif yazabilir miyiz?
Well, let's stick with this choice for the time being, and let's write the equations, and then let us choose some other directions and see how it changes. I mean, I chose this one. Maybe he will choose some other direction, so that's fine. Let's see how he will solve it.
So we keep changing the direction of the current for
I'm not changing the direction of the current. I'm changing the positive direction of the current.
That's what I meant. For every separate wire. For every separate wire.
Yes? And if I want to be even meaner, I can even split this wire into here. I can choose one direction of the current for this piece of the wire and another direction for the other piece of the wire. That's also valid. I wouldn't do that, but it's valid. Now, okay, so this is, now we had three unknowns, so we need three equations. This is one of them. Let me just reorganize it a bit. So it tells me that I2 times R1 minus I3 times R2, this is equal to epsilon 2 minus epsilon 1. This is my second equation. I need one more. I can again take this point and go around this larger loop. Now, if I go around that larger loop, okay, from this point up to this point, what is the potential drop? 0, there's no resistance, there is no potential drop anywhere. From this point to this point, what is the potential drop? Minus I1 times R3. The potential difference across a resistor is I1 times R3. That's I1. Since I'm going in the opposite direction as the positive direction of the current, so it's just this minus sign is because of that. And from this point to this point, what is the potential drop? Minus epsilon 3. From that point to this point, what is the potential drop? There is no current. From this point to this point, what is the potential drop? Plus epsilon 1. And from this point to this point, what is the potential drop? I2 times R1. It is again positive. And we have another equation now. I1 minus minus I1 R3 plus I2 R1. This is equal to epsilon 3 minus epsilon 1. Well, we have 3 unknowns, 3 equations. The rest is algebra. You can just solve for I1, I2, and I3 using all these 3 equations. And no matter how complicated your circuit can be, you can just apply exactly the same principles, and that would be enough to obtain all the currents in your wires. Any questions? Okay, let's change the directions. No. Once you choose the directions over here in your circuit, the signs in these equations are fixed. You cannot play with them. It's like if you choose this direction as the positive direction of your position, you cannot say that the position of this book is minus 1 meters. It's in plus 1 meter. Its sign is fixed once you choose your positive direction. Let me just take the same circuit. Okay, what would you like to change? Somebody? Which directions would you like to change? Well, if you change all of them, it's not interesting. I mean, you get the same equations, exactly the same. You want to change I2 and I1?
Bence sadece ayrılmak istiyorum.
Okay, let me just pick someone. Yes. Which one do you want to change? No, him. I1. Okay, so you want to change I1. No, okay, this is I1. You want to change its direction. You want to change something else? That's enough? Okay. Don't be afraid of those. Okay. Now let's look at that point again. What is the sum of the currents entering that point? I1. There's just one. What is the sum of the currents leaving that point? I2 and I3. So this is our first equation. We need 3 of them. Well, I can also write this as 0 is equal to I2 plus I3 plus minus I1. Now, if you compare it with the previous result, you say before it was I2 plus I3 plus I1. Now it is I2 plus I3 minus I1. Now that kind of makes sense because in this new convention, if our current is 5 amperes, in the previous convention we should call it minus 5 amperes because the positive direction has been changed. For the same current we use a different numerical value because the directions have been modified. And in the other equations also we will see exactly the same thing, just I1 will be replaced with minus I1. Now let's continue. We start from that point, we go around this small loop. Okay, the potential drop from here to here. 0. Well, since this loop doesn't even involve I1, it will be just identical. Plus minus I3 R2 plus minus epsilon 2 plus epsilon 1 plus I2 R1. In fact, this is, as I said, this is identical to the previous one. I2R1 minus I3R2. Well, I2R1 minus I3R2 is equal to epsilon 2 minus epsilon 1. It's identical. It doesn't involve I1. Now let's look at the other one. Okay, let's start from this one, this point. Again, from this point to this point, the potential drop 0. From this point to this point, the potential drop plus I1 times R3. From this point to this point, minus epsilon 3. Now from that point to this point, 0. And from this point to this point, the potential drop, is it minus or plus epsilon 1? Well, we go from the positive terminal of the battery to the negative terminal of the battery, so the potential drops. So the potential drop is just epsilon 1. And from this point to this point, is I2 times R1 is the potential drop, this I2 times R1, so it's plus I2 times R1. Well, let's compare. Before we had this equation on the top. Now we have this equation. So if we compare, here we had minus I1 R3. Now we have I1 R3. I1 changed its sign. Then we have minus epsilon 3, plus epsilon 1, plus epsilon 1, plus I2 R1, plus I2 R1. So everything is equal. The only difference is I1 has changed its sign. And as I said, that is expected because we just changed the positive direction of I1. In the previous convention, a current that which is represented by 5 amperes in this convention should be represented by minus 5 amperes in this convention. So that is why there is this sign change. Now, any questions on these signs? How we choose these signs? These are the Kirchhoff's rules. Well, this might not be the proper way of writing the name, but it's the Kirchhoff's or Kirchhoff's rules. Well, basically we have the loop rule. So if you go around any loop, the potential drop, or you can prefer to write the potential increase, or you can say the sum of the potential changes should sum up to 0, which is called the loop rule. This is one rule that we have been using. The second one is that the sum of the currents entering a point is equal to the sum of the currents leaving that point. Let's say that is the current rule. So these two that we have been using to study the currents in circuits are what's called the Kirchhoff's rules.
There was an example. They go parallel. They come back together. There's a 1, 2, 3, 4 of resistors, and then there's one in the middle there. I was curious about that. Yes.
So what is the equivalent resistance? R1, R2, R3, R4, R5. Now in these circuits, They are not connected in parallel. They are not connected in series in general. Now your friend over here is just making this sign, saying that if the ratio of the resistors, these two resistors, is equal to the ratio of these two resistors, then there is no current running through this R5 and you can just remove R5. But of course, in general, if the ratios are not equal, you cannot do that. If you cannot remove R5, there is no simple way of solving it. But still, Kirchhoff's rules will be valid. So we can use the Kirchhoff's rules to determine the currents in all of these wires. Let's say this is the total current I. Let's say this is epsilon. Our equivalent will be nothing but defined as epsilon over I. So if you can determine this current over here, then you can determine the equivalent resistance. So the task is, how do you determine the currents? Well, we can just start by choosing some positive directions and giving some names. Let's say this is I1, this is I2, this is I3, this is I4, and this is I5. And this is again I. So we have 6 unknowns. We have to write 6 equations. Well, in general, it will be a long calculation, but kind of trivial in the sense that it's just technical algebraic manipulations. After you write the equations, Kirchhoff's equations. You want that way? Okay, that's fine with me. Let me change it. So you want the current to go both up and down? No, let's just say that from this point downward, the current is going down, and from this point upward, the current is going up. Let's call that I4 prime, if you like. But let's look at that point over here. What is the sum of the currents entering that point? 0. What is the sum of the currents leaving that point? I4 plus I4 prime. So I can already solve this equation. I4 prime is equal to I4 minus I4. So I can just I can choose to express all my solutions in terms of equations in terms of I4 or in terms of I4 prime, as you wish, whichever one you want. But I would rather express everything in terms of I4. Why? For no reason. You can choose I4 prime. But if you are expressing everything in terms of I4, then this tells me that I4 prime should be, well, if I4 is positive, then I4 prime should be negative. It means it should change its direction. So rather than increasing the number of unknowns and having such trivially solvable equations, I just set one direction for all of that wire. And which direction you choose, up to you. Again, I'm not choosing the direction of the current. I don't know. I'm just saying that I will say that if I4, the current in this wire is running downward in that figure, then I will call that a positive current. If it is running upward, I will call it a negative current. That is the only thing I'm choosing. What is the direction of I4? I don't know. The equations should tell me. Now let's write down the equations. First, let's start with the conservation of the current. At this point, what can you say about the currents? What is the sum of the currents entering that point? I. The sum of the currents leaving that point? I1 plus I2. Okay, this is one equation for the 6 unknowns I have. Let's look at this point. What is the sum of the currents entering that point? Entering that point. I5 plus I4. Sum of the currents leaving that point? Just I. Oh, sorry, it's I3. So that's my second equation. Now let's look at this point. What is the number of currents entering that point? The total current entering, the sum of the current entering that point, the top one. This one. It's just I1 is entering. And I4 and I5 are leaving that point. Their sum is I4 plus I5. This is my third equation. Well, let's also check this point. The sum of the currents entering that point, I2 plus I4. The sum of the currents leaving that point, that is I3. Now let's see. I have 4 equations. First of all, are they all independent? Let me just subtract this equation from the second one. This one minus, okay, no, let me just equate these two. They are both equal to I, so they have to be equal. And that tells me that these two equations already tell me that I1 plus I2, this should be equal to I3 plus I5. Or I1 minus I5 plus I1 plus I2, this is equal to I3. Now what I did is I took this equation, moved I5 to the other side, so I have I1 minus I5 plus I2, this is equal to I3 is left. But I1 minus I5 from this equation is nothing but I4. I4 plus I2, this is equal to I3. This is the fourth equation. So those 4 equations are not independent of each other. So here I have 6 unknowns, right? 1 to 5 and the total I. I have 6 unknowns. I need 6 equations. Here, although there are 4 equations, there are only 3 independent ones. I need 3 other independent equations. And those will be from the loop rule. Let me just take this circuit. Now you can choose any 3 loops you like. I will choose this one as one of my loops. This is 1. Let's say this will be my second loop. This is 2. And then I will choose this one as my third loop. I mean, you are free to choose whichever one you like. Why did I choose those things? Well, because they are easy to draw. They will not be crossing each other. There is no other motivation. Just choose whichever 3 you will see. Let's start with the first one. I start from this point. I go to this point. What is the potential drop? It is I2R2. This is the potential difference across the resistor. But I'm going against the direction of the current if I2 is positive. So if I2 is positive, the potential drop should be negative. From this point to this point, I'm going in the same direction as the current if I1 is positive. So the potential drop is just I1 times R1. And then from this point to this point, it is I1 times, now this is the current running through, this is I4 times R5. It's the potential drop is just I4 times R5. This is equal to 0. This is from 1. No, 0. R5. Now let's look at loop 2. You see, in loop 1, for example, I go from this point to this point. In loop 2, I go from this point to this point. That also doesn't matter. So let's see, as I go from this point to this point, what is the potential drop? It is I4 times R5, that is the potential difference across the resistor, but if I4 is positive, I am going against the current, so it should be negative. Plus, as I go from here to here, what is the potential drop? The current is I5, the resistance is R3, the potential drop is just the sum of the two. And since I'm going in the same direction as the current, if I5 is positive, that's positive. And from this point to this point, the current is I3, the resistance is R4. I'm going against the current. I go from that point to this point. It's against the current if I3 is positive. So if I3 is positive, I should add a minus negative number. This is again 0. So that gave me 5 equations. Now from this third loop is the 6th equation that I will obtain. So let's see, from this point to this point, what is the potential drop? 0. From this point to this point, the potential drop? I2 times R2. Current is I2, resistance is R2, so I'm going in the same direction as the current. From this point to this point, I3 times R4. And then I'm here. From this point to this point, what is the potential drop? 0, there's no resistance. And from this point to this point, the potential drop? Minus epsilon. This is equal to 0. So these are my 3 other equations. I had 3 before, now I have 3 more. I have 6 equations, and the only thing I need to do is just solve for the capital I. Solve for the 6 unknowns, one of which is the capital I. And so that gives me the capital I. Once I determine the capital I, once I determine this capital I, epsilon over I just gives me the equivalent resistance of this system, where the resistors are neither in series nor in parallel. Then if you ask the question, what is the condition under which I4 is 0? Then you can just solve these equations for taking I4 equal to 0. Solve those equations, and those equations will be consistent with each other under a certain case, and that is your condition under which I4 is equal to 0. Now, any questions on these ones? Okay, let's give a 10-minute break now.